from TU Wien. He's going to talk to us about combinatorial properties of open covers, dense sets, and forcing.
So can you hear me? Yep. Good. So first of all, thanks to organizers. It has been kind of a great conference until now, until this talk. And thanks to all of you for coming to my talk. So today I will speak about combinatorial properties of open covers and some related stuff. So some of you might know it under name selection principles. That's just an equivalent name for just another name for combinatorial properties of open covers. And okay, just as a motivation, let's start with something that everybody knows. A space is compact if every open cover has a finite subcover. Now, a space is sigma compact if it can be written as a union of countably many compact spaces. And now imagine that you are given a task to characterize sigma compact spaces in terms of open covers. So I would expect that most of you will come out with the following property, which says that for any sequence of open covers of the space, you can select from each open cover finite portion such that all together they cover the whole space. Actually, every sigma compact space has this property. Just select from cover number n, finitely many elements which cover compact number n, and you are done. Well, those of you who are more careful might invent a bit stronger property, namely that not only you cover your space, but you cover it by this union in a very strong sense, namely that each point gets covered by all but finitely many elements all but finitely many of these unions. Again, sigma compact spaces have this property because without loss of generality, you may assume that your sequence of compact spaces is increasing, and then each point gets covered from some point on. Good. But so such strong covers we call gamma covers. It's like gamma rays, right? They are very powerful. And good. So the first attempt, those who went for the first attempt would define the Menger property. Those who went for the second one would define the Hurewicz property. Both of these, as the name suggests, were defined long ago, actually in the 20s of the previous century. And as we have already discussed, every sigma compact space is Hurewicz, every Hurewicz space is Menger, because we just demand that your open cover is stronger. And each of them are Lindelöf, because if you are not Lindelöf, so if you have an open cover without any countable subcover, then just look at a sequence where each covers are just this one, and then no matter which finite portions you select, you will never be able to cover the whole space, because these finite portions will at the end give you just a countable subset of this cover. So this is kind of properties I would like to discuss today. And examples, well, not all Lindelöf spaces are Menger. Namely, the classical example is the Baire space, so homomorphic to irrationals. And here is the sequence of open covers witnessing that it fails to be Menger. Namely, the open cover number n just tells you what is the nth coordinate of the sequence. And now if you just think a bit, if you select finite portion from each of these open covers, then on each coordinate you will have some finite bound. And if your function from omega to omega is always above this finite bound, this function, this sequence will never get covered by any of these finite selections. Good. So actually, if you would like to construct counterexamples, say, so both of them conjectured that the properties they invented are equivalent, at least for metrizable spaces, for sigma compactness. And they were right for all nice spaces, namely for analytic sets of reals. Let me remind you that analytic means that it's just a continuous image of the Baire space of irrationals. The Menger property is equivalent to the sigma compactness. So all these properties down, they just collapse to sigma compact spaces. But in L, in the constructible universe of Gödel, you have already co-analytic Menger subspaces of the Baire space, which are not sigma compact. And so actually, and we will see later that you can distinguish all these properties outright in ZFC. But when you study these properties, it's very there is a relation which always comes with them, which kind of helps to analyze them, namely the relation of eventual dominance. You say that one sequence of natural numbers is eventually dominated by another if it's almost everywhere. So you allow only for finitely many mistakes when the first sequence is above the second one, but from some point on, the second one should be above this one. And Hurevich proved in 1925 that zero-dimensional Lindelöf space has the Hurevich property if any continuous image of this space by map into the bare space is bounded. Bounded with respect to this. Whenever from now on, whenever I say bounded or dominating, it's always with respect to this eventual dominance relation. Now, the similar characterization is true for Menger spaces. Space is Menger if and only if all of its continuous images in the bare space are not dominating. Good. Now, there are two cardinal characteristics associated to this eventual dominance relation, namely B, the minimal cardinality of an unbounded subset of the bare space, and the minimal cardinality of the dominating subset. Of course, B is less or equal than D, because if you're dominating, then you're automatically unbounded. That's the power of logic. And by characterizations of Hurevich, we immediately have that if a space has size less than B, it must be Hurevich. And if the space has size less than D, it must be Menger. So we already have some consistent counterexamples. We've got non-sigma compact spaces which have property Menger and Hurevich if B and D are above omega 1. Okay, but what happens under CH? Under CH, all these two cardinals are just omega 1, and we end up just with countable examples. And, well, that's not interesting. Let's see, under CH, actually, the counterexamples were found even before the properties were introduced. So let me remind you that a subset of the bare space is a Luzin set if it itself is uncountable, but it has countable intersection with any meager set. So meager, it's just the short name for first category. And every Luzin set is Menger because it is concentrated. Let me draw what does it mean. Creating a mess here. So we say that a topological space is concentrated on some countable subset of it Q. So the space is like the whole piece of paper, that if and only if for any open neighborhood of U, of Q, the outside of this open neighborhood, you've got only countably many spaces, countably many points in this space. And now, so this is concentrated spaces. Now notice that any concentrated space must be Menger. Why? If you give me a sequence of open covers, I use, say, open covers with even numbers to cover this countable set on which it concentrates. So the part of the space which is still uncovered, it's some complement of some open neighborhood of this Q. And that's just countable. So I use the remaining covers to cover this countable set one by one. And our Luzin set is actually concentrated on any dense subset of the bare space. Why? You give me a dense subset of the bare space, I take any open neighborhood of this subset, the complement is closed nowhere dense, and the Luzin set has countable intersection with any meager set, in particular with any closed nowhere dense set. So Luzin sets are concentrated, and that's why they are Menger. That was the busy bit. Now, just dual notion for measure. It's a Sierpinski set. Set is Sierpinski if it is uncountable and has countable intersection with every measure zero set. And Skippers proved a useful characterization of Hurevich spaces, which actually, I will say some equivalent formulation of it. It says that whenever you put the space is Hurevich, if and only if, whenever you put it into a Čech complete space, then it is contained in a sigma compact subspace of that Čech complete space. And from this characterization, we immediately get that Luzin sets are Menger, but not Hurevich. Why? Because imagine that you've put your Luzin set into in the bare space. Okay, it's Čech complete, because it's just Polish. Select any dense countable subset of the Bayer space which is disjoint from your losing set. If your losing set were Hurewicz, by this theorem of Skipper's, it would be contained in a sigma compact subset disjoint from this countable. But sigma compact disjoint from countable dense must be meager. And that's contradiction because losing sets kind of run away from every meager set. They have at most countable intersection with them. So that was easy. A bit more tricky proof is to prove that Sierpinski sets are Hurewicz. And more generally, of course, you can introduce these cardinal characteristics into the definitions, say demanding that with any meager you have intersection of size less than some kappa, where kappa is some cardinal, or with every null set you have intersection less than kappa. So this gives you notions of B, Sierpinski, and D losing, and they again are Hurewicz and Menger. So there is some place to play with cardinal characteristics here. Good. So we can get examples also by forcing. So if we had some topological space in the ground model, if you add uncountably many coin reals, then the space becomes actually Menger in the extension. And maybe let me stress what I mean by this space in the extension. In the extension, I used topology from the ground model as the base for a new topology in the extension, because of course you may get more open sets just because there are more subsets of tau, and in the extension any union of elements of tau must be also open. Good, so the proof consists of two steps. The first step is non-trivial, that X remains Lindelöf. But once you know that it remains Lindelöf, it's very easy to prove that it becomes Menger. So this part is due to Dow. And why does it become Menger? Because if you are given a countable sequence of open covers of this space, since this Lindelöf, you may assume that all the elements involved into these covers are in Tau, in the topology from the. And then this sequence lives in the intermediate model, which involves only countably many coin reals. And I'll take any fresh coin real which comes after and use it to pick an element from each open cover. And just by genericity, this selection will actually prove that it will cover the whole space, and it will cover it actually in the stronger sense, because we didn't select finitely many from each of them, but just one. So we will come to this property where you select just one element slightly later. And folklore, which is, again, if you have a ground model set of reals and you add many dominating reals, then you get Hurewicz space. So by forcing, you can turn, with very gentle forcing, you can turn your ground model Lindelöf spaces into Menger spaces, and if you put more force, you can get even Hurewicz. Good. Now, so we know already counterexamples using cardinal characteristics. We know counterexamples to the implications using CH. Now, actually, all of these properties which I've like sigma compact, Hurewicz, and Menger can be distinguished in a strong sense outright in ZFC. So Fremlin and Miller in '88 proved that there are Menger non-sigma compact sets of reals. Then used Miller, Skippers, Sheptytsky in '96 proved that in ZFC you've got a Hurewicz non-sigma compact set of reals. Bartoszyński and Saban in 2006 improved it, that actually you can even get here that all finite powers of this subset have the Hurewicz property. And then Haber and Paul in 2002 proved that there is a set of reals whose all finite powers are Menger and not Hurewicz. So basically all of the properties in that row can be distinguished in ZFC. And for curiosity, if you go to a yet stronger property, namely to the Menger property, you can associate a game in which the first player gives you an open cover and the second responds by choosing a finite subset of it. And now again, the second player wants to cover the whole space. If the second player has a winning strategy on a hereditary Lindelöf space X, in particular on a metrizable space X, then X must be sigma compact. So if you push slightly further, you collapse it to the sigma compactness. Good. Now, how do people get this ZFC counterexamples? You can get all of them by slightly maybe more sophisticated use of concentrated sets. So remember, concentrated sets, that are sets such that outside of spaces such that outside of some countable subset, if you take an open neighborhood of some countable subset, outside of it you have at most countably many points. And now kappa concentrated, you just introduce this parameter, cardinal parameter kappa, into this definition by demanding that on outside of any open neighborhood of this countable set Q, you've got fewer than kappa many points in your space. Good. Now, if you are deconcentrated or kappa concentrated for some kappa less or equal d, then your union with this countable set must be Menger. Why? For the same reason. First, you cover this countable set using half of your open covers, but outside you've got fewer than d many points. And we know that any space of size less than d is Menger, so such unions are Menger. And, well, there exist deconcentrated sets outright in ZFC. Well, why is that? Let's fix a dominating subset of the bare space and inductively construct yet another sequence consisting of this upper arrow means of increasing elements of the bare space, such that every sequence number alpha is not dominated by any of elements of this dominating set with smaller indexes. This is possible by the definition of D, because there are just fewer than D many sequences that you would like to be not dominated by them. And if you view it as a subspace of, now here you just put omega into omega plus 1 and view it with the topology like of, with the ordinal topology, so it becomes a convergent sequence with omega being the only non-isolated point. And if you look in this space at all non-decreasing sequences, it becomes just a topological copy of the Cantor set. And here, this set S is very easy to check that it becomes deconcentrated on the countable dense set consisting of those sequences which eventually attain omega. Okay, so this countable set, and we've got in ZFC a deconcentrated set, and that's why we've got a Menger not sigma compact in ZFC. And one can also prove outright in ZFC that there exists a B-concentrated set, and well, if your B-concentrated set is chosen carefully, its union with Q will be Hurevich. It's a result of Bartoszyński and Shelach from 2001, and for curiosity, oh no. And then it was improved by Bartoszyński and Szaban to prove that all finite powers of some carefully chosen B-concentrated set together with Q are Hurevich. And for curiosity, the statement that all B-concentrated sets are Hurevich is actually independent. We know that it's wrong under CH. Actually, it's wrong under B equal D, but from what we have heard before, it implies that it's wrong under CH, because under CH, losing sets are B concentrated because B becomes omega 1. And we know that losing sets can never be Hurevich, but this statement is true in the Miller model. Good. Now, actually, it's just too few to consider two properties during such a long talk, so I will introduce more properties. And these will be properties which will be very strong in the sense that in some models, consistently, they will all collapse to countable spaces. Okay, so an open cover of a space is an omega cover if, for any finite subset of the space, it is completely contained in one single element of your cover U. So, for instance, the open cover of the real line by intervals from -n to n will be an omega cover. But if you look at the open cover by intervals of length, say 2, it will not be an omega cover because 2 points 0 and 3 will never get covered.
So it should be omega cover, not gamma cover.
It is omega cover.
The last line, which gamma covers X.
Oh, no, it's all right. It's all right. So a space X is a gamma space. If for any sequence of omega covers of X, you can select one element from each of them, which not only covers the space, but covers it in a very strong sense, which is in the gamma cover of X. And gamma cover, it was on the first slide. Remember, it's a covering in a very strong sense, namely that any point gets covered by all but finitely many elements of the cover. No, I think it's all right the way it's written. So in the Rothberger property, it's just like Menger, but select one. So you've given a sequence of open covers, and you select one from each of them, and you would like to cover your space. And the gamma spaces were introduced by Gerlitz in 1982, and they proved in the same paper that they must be Rothberger and Hurewicz, and all finite powers of gamma sets are actually gamma sets. Now, this is not so obvious because, say, in the Rothberger definition of the Rothberger property, you've got weaker, you need, as an outcome, a weaker property, right? Here you demand to be gamma cover at the end, and here you just say that it's a cover. But the sequence of open covers in the gamma space is much more restricted that you get as an income. Here you put this additional property of being omega covers, and here you just get any open covers.
Sets and gamma space is the same.
Yes, it's just, yeah, actually sets is shorter than spaces, so that's why I like it. Good. So, but if you work not actually very hard, you can prove that each being gamma set is a really strong property, because not only you are Rothberger and Hurewicz, but then in all finite powers, this is also true. Good. And this is the diagram. We've got two more properties. I guess these three all of you have known before. So gamma spaces are Hurewicz and Rothberger, and Menger is the weakest of these properties. So just remember the shape of these four. Just that gamma is the strongest, Menger is the weakest, and no matter where you place these two, it's actually an isomorphic diagram, so it's very easy to remember it. This is how all the properties we have introduced thus far are related. And this is in the Lyubomyr model. All Rothberger spaces are countable, but we will come closer. We'll discuss closer this fact. So that's why, unlike the upper row, they never collapse outright in ZFC. You construct all possible counterexamples in between of them, but the lower row just collapses to being countable in the Lyubomyr model. Good, but, and everything you can distinguish, at least consistently, all the properties which appear here. The only unsolved, which is the question which is a bit annoying, is the following one. Is it consistent that every Menger subset of the Cantor space, which has no copy of the Cantor set inside, is Rothberger? Because it's nearly a simple exercise that if you contain a closed copy of the Cantor set inside, you're not Rothberger, because all the properties, like covering properties, are inherited by closed subspaces. So you can cheat by saying, let's take the whole Cantor set. It's Menger because it's compact, and it's not Rothberger. But if you don't allow, we are honest people, we are not allowing for cheating. If you just exclude this very easy way to producing counterexamples, then I think that it's unknown how to produce such a counterexample in ZFC. Good. Now, I've introduced many properties which might seem a bit funny to you. Let me now motivate why are they actually interesting, where do they appear, and how are they connected to some other facts. So the gamma spaces, gamma sets, were introduced just because they characterize those spaces for which the space of continuous functions with the topology of pointwise convergence has the Fréchet-Urysohn property, and Fréchet-Urysohn property is kind of a holy property. So it makes immediately gamma spaces very interesting, because it's just, you characterize it, it's dual notion to Fréchet-Urysohn for the spaces of functions. Okay, now the motivation to the Rothberger property comes from the strong measure zero sets. Let me remind you that a set of reals is strong measure zero if, whenever you give me a sequence of positive epsilons, I am able to find the sequence of centers such that if I look at the balls with radius of these epsilons around my centers, I cover the whole set. So in particular, every countable set has countable metrizable space has strong measure zero, because then I don't really have to take care of your epsilons. I just cover the whole space by my centers. And the notion was introduced 90 years ago by Borel. And it turned out, it seems like funny, but it turned out to be very, very important for the development of the set theory later, for the following reason. Well, Borel asked whether all strong measure zero sets are countable, but then immediately Sierpinski observed that losing sets have strong measure zero, and the question whether consistently all strong measure zero sets can be countable remained unsolved until late 70s, when Laver produced his famous Laver model, in which actually all these guys are countable. And the Laver model was the historically first countable support iteration of proper forcings. And then later, this method has been systematized by Scheller, who actually introduced proper forcing. And now countable support iterations, it's a tool that is very important for the set theory of reals. And I guess it's very much, this property kind of helped to go in the correct direction. Good. But, well, Rodberger observed that this strong measure zero is not a topological property. So you may have under CH two metrizable spaces, which are homomorphic as topological spaces, but one of them has strong measure zero, another does not have. And then he introduced his property, of course, not under the name Rodberger property, and as a topological property, which is very similar to it. Because if you think about this strong measure zero, it's just like Rodberger property, in which the sequence of open covers is very restricted. They must be just such covers that for each of them you've got this epsilon. It's a cover by epsilon balls. And Fremlin and Miller proved that Lindlow space is Rodberger if and only if for any metrizable image of it, the range must have strong measure zero. So you may think of Rodberger property being just a topological counterpart of strong measure zero. Good, so this is motivation for these two. Another motivation for Rodberger comes from a work of Skippers, and the topological space has this, space X has this arrow property. If for any omega cover of it, if you color, I'm sorry, there should have been two here. If you color pairs of elements of this omega cover into two colors, then you've got an omega subcover of it, such that the restriction of this coloring function to the pairs inside of this V is constant. And then Skippers proved that the space satisfies this property if and only if all finite powers of X are Rodberger. And this is just the beginning of that. There are many more results in this direction by Skippers and many other people. And another thing is, again, from Ramsey theory, it's, let me mention to you the following result of Szaban. So if you have a topological space and you cover not only open sets, but also pairs of open sets by some finite number of colors. Now suppose that you've got that the space is Menger and your cover is Ridge. So the point infinite means that any point of your space is covered by infinitely many elements of your cover. Good. Then you can find finite subsets of your cover, such that if you say Vn is a union of the nth finite subset, these Vn's have the following property. Well, they're all mutually different. Not only they're mutually different, but their unions are different if you take indexing sets such that the maximum of one of them is the minimum of another. And, well, any finite union of these Vn's gets the same color. And any pair of such unions gets the same cover if, again, the indexing sets satisfy the same condition. And now, until now, it would be just easy the consequence of Millikan-Taylor theorem. And actually, you would get, it's easy to get Millikan-Taylor from this bit. So until now, nothing new. But the last condition makes it kind of interesting that these finite unions will be actually a cover of the whole space. So you may think of this result as a topological version of Millikan-Taylor. And actually, it's unknown whether Menger is needed here. There are non-Menger examples where this is not true. But for instance, it's unclear whether this theorem is true for the Baire space, our best example of non-Menger space. Good. So the third motivation comes from Mathias forcing. So a filter is let me remind you, a filter is a family of infinite subsets of omega, which is closed under finite intersection and taking supersets and finite modifications. And, well, to each filter you can associate a poset consisting of pairs. So the first coordinate is just the finite bit, and the second coordinate is an infinite element of your filter, which is above the maximum of this finite bit. And you say that one condition is stronger if another if the finite bit grows, but as an end extension, the infinite bit shrinks, but the portion that the new portion of the finite bit must get into the old infinite part. And this is the kind of probably the most, it's called Mathias forcing associated to F, and this is probably the most simple way to produce by forcing a pseudo intersection of a filter F. Namely, if you have a generic filter, look at the union of these finite bits of all the conditions in the generic filter, and that gives you the pseudo intersection. And as applications, you may, well, if you apply this to filters which are dual to Met families, you may kill Met families with this filter. And well, you can make, if you apply this to an ultra filter, you can make ground model reals not splitting and etc. But I guess one of the most often considered questions is that when this Mathias forcing does not add dominating real. So recall that a poset adds a dominating real if it adds a dominating real. So if it adds a real which dominates all ground model reals. And okay, examples are Lever and Heckler forcing, and Miller and Cohen are very gentle. They don't add us dominating reals. And the theorem of Kanjar says that under D equals C, one can construct an ultra filter F such that the Mathias forcing does not add a dominating real. This is sort of a strong result because in the ultra filter you've got like half of your Cantor set. So you know that you can shoot a pseudo intersection through half of your infinite sets, but still not adding dominating reals. And well, motivated by this, Guzman, Hrušek, and Martinez said that defined filter F to be Kanjar if the Mathias forcing does not add a dominating real, and if you want to be more specific and say which ground model set of reals you would like to keep unbounded, you can use it as a parameter and define your filter to be Bikanjar if the Mathias forcing does not add a real which dominates all elements of this family B. Good, and it turns out that all these guys just studied Menger and Hurevich filters with the following results of Zdomskyy, Repusch, and myself. So the filter is Kanjar if and only if it is Menger with respect to the topology inherited from the Cantor set, and the Mathias forcing is almost omega bounding. That's a notion introduced by Schelach, and well, I'm not going to define it just because it's very easy to. The original definition is kind of more technical, but it's easy to see that it's equivalent to keeping all ground model unbounded sets of reals still unbounded in the extension. So if F is Bikanjar for all unbounded B, and this happens if and only if F has the Hurevich property. Good, and it allows us to prove that all analytic filters must be sigma compact as long as their Mathias forcing does not add dominating reals, and it's kind of improved a bit the previous result of Guzman, Hrušek, and Martinez. And yet another result of this kind. So Zdomskyy, Guzman, and Hrušek proved that the Mathias forcing does not add eventually different real. So real is eventually different if for any ground model real, our real is from some point on takes different values. Of course, dominating reals must be eventually different because they must just escape from ground model reals upwards, but eventually different are allowed to go both ways. So that's kind of slightly weaker notion. So Mathias forcing does not add eventually different reals if F is Rothberger, but not with the topology inherited from the Cantor set, just because it is impossible for non-trivial filters. In non-trivial filters, you always have many copies of the Cantor set inside. So here you say about Rothberger property of some weaker topology, namely generated by upper cones of finite subsets of omega. And then, as a result, actually it's lots of work using some games due to Laflamme. They proved that if F is, well, Borel, then the Mathias forcing does not add eventually different reals if and only if F has countable base. Well, but in this case, the Mathias forcing is just the Cohen forcing. So the only way the Mathias forcing for Borel filters cannot add eventually different reals is being forcing equivalent to the Cohen forcing. And using actually our previous thing, it was possible to extend it to analytic filters. And as you know from the talk of Andrea Medini, it's not always easy to prove for analytic sets what you know is true for Borel. Good. Now, question. Suppose that A is a mad family which remains mad after you add many coin reals. So, in other words, you cannot destroy it with coin reals. So, can it be extended to a Hurewicz filter? I mean, not the mad family, but the dual filter, the filter generated by the complements of elements of this mad family. Now, why I find this question interesting? Because there is another question which is kind of a real question. This is like, okay. Another real question, it's a question due to Reutemann. I was unable to find when it was posed. It asks, is it true that the inequality D equals omega 1 less than A is consistent? Now, A is just the minimal cardinality of a mad family. Now, why did I make omega 1 red? Just because there is like a very powerful method developed by Shelach and then further developed by Brendel, Fischer, Mejia, and many other people. And it allows you to get the consistency of the inequality D less than A, but above omega 1. And in case when you say D is omega 1, it's still unknown how to do it, despite all of the efforts of these people. And well, if the positive answer to this question, if the answer to the question I've put above is positive, then, well, I don't know how to solve the Reutemann's question, but I know how to solve some kind of a baby version of a Reutemann question, which is still open despite of all the methods developed for. It seems that all these methods developed for cardinals above omega 1, they can very little say about what happens if you would like to put the lower cardinals at omega 1. Good. So let me put the diagram once again. And now, after we finished with motivation, actually the subject might be kind of interesting internally. It's not only motivation which makes it interesting. There are kind of internal questions. And one of the internal questions I'm interested in is preservation by finite products. So you have some of these properties, and you ask, can the product of the spaces with the properties must it have the same property? Or maybe you can fail, say, you may find the product of gamma spaces which are not Hurewicz, which would be even better as the failure of Hurewicz property being preserved by finite products. Okay, so once again, please memorize these four guys. Gamma space, the strongest, Menger, the weakest, and the others two are in between. And that all finite powers of gamma spaces are gamma spaces. Well, Todorcevich proved outright in ZFC that there are two regular gamma spaces such that the product is not even Lindelöf, so in particular, it's not Menger. So in ZFC, you get the spaces with the strongest property, whose product does not have even the weakest one. Like, seems end of the story, right? Because what can be better? You cannot do anything better here. But wait a moment. Some people just say, look, all these properties were invented just for sets of reals. That's the origin where it comes. So this is a very nice result, but this is not really what we want. We would like to see what happens if we just speak about sets of reals. Well, some other people just say, maybe sets of reals is too restrictive. We would like to consider some wider classes of topological spaces, which are still kind of have nice properties guaranteeing that any finite product of spaces of this kind will be still Lindelöf, right? So it doesn't have to be just subsets of reals. But actually, both of these groups go in the same direction. I guess you don't have to read this. The meaning of what is written here, that if you fail, if you've got two spaces which has one of these properties, and the product fails to have some other one, but is still Lindelöf, then you can somehow, using some general nonsense kind of proof, reduce these spaces to sets of reals which have exactly the same properties. So from now on, the covering properties will concentrate on sets of reals. Good. So typical non-preservation by products proof is, I selected this result of Just, Miller, Skippers, and Sierpinski, which says that there are two Sierpinski sets whose product is not Menger. Remember, Sierpinski means that you run away from every null set. You're uncountable, but your intersection with every null set is countable. Well, under CH, well, you fix a countable dense subset of the Cantor set. and enumerate its complement. Now, in the construction of Sierpinski set, by transfinite induction on each stage alpha, you are allowed to pick your point outside of a given measure 0 set. So you've got measure 1 possibilities to pick a point. Now, what you do at stage alpha, you make sure that you, by the points that you add to one of your Sierpinski sets and to another, their sum, there is, of course, a natural structure of topological group on the contour set, that their sum can never be an element of this countable dense set. Another thing that you have to take care that eventually, if you take at all their mutual sums, you pick all the points from X alpha. So as you see, you've got at each stage only countably many restrictions, plus the restriction to put your point outside of some measure 0 set. Altogether, at each stage, you have huge freedom. You can pick your points from outside of some measure 0 sets. That's why this construction gives you, at the end, 2 Sierpinski sets, whose sum inside of the group is exactly this complement. But the sum inside of the group is a continuous image of the product. So the product can be mapped continuously on this complement. This is just contour set, remove countable closed subset. This is just a copy of the bare space. Okay, so we've mapped our product onto the bare space. It cannot be Menger because all the properties are preserved by continuous images. So this is like a very typical proof. It may get slightly more complicated though, but many of the proofs is just the version of it which you have to take care of more things and then it becomes slightly more complicated. Good, and well, Skipper similarly, in the similar manner, proved that you've got 2 Luzin sets and then they are Rotberger whose product is not Menger, and all of their finite powers are in addition Rotberger. And then Arne Miller was Boas Taban and myself, but the crucial idea comes from Arne Miller. Under CH constructed 2 gamma sets of reals whose product is not Menger. So we've again got the same kind of ultimate failure, but with this very strong assumption. And of course, you cannot get it in ZFC because gamma sets collapse to countable spaces in the Lyubomyr model. So whenever you would like some failure where your properties that you get on this side are either gamma sets or Rotberger, it must be some additional set theoretic assumption present in the formulation. Good, and there's a really kind of result in a different direction. Barman and Dow proved that PFA implies that any finite product of gamma sets of reals is Menger. So you see, usually if you have such a construction from CH of sets of reals, if you look close at it, you identify the cardinal characteristics which are responsible for this construction. So like usually whatever, in most of the cases, whatever you can do under CH, you can do it under Martin's axiom, which is a weaker statement than PFA. But not here. Here, no cardinal characteristics will ever help you. I'm sorry, it just means that I've got 10 more minutes, I guess. So, good. So this is one of the, if you know any other such examples, please tell me. I think that's the only one of this kind that I know that you do something under CH and cardinal characteristics will never help you to do it. Good. So, but you can anyway get a similar result in models of non-CH by adding many coin reals, simply because gamma sets are preserved by coin reals, and if the product were not Hurewicz in the ground, not Menger in the ground model, it can never become Hurewicz. So we've got slightly weaker statement. We've got gamma sets whose product is not Hurewicz. Now, well, what if you just don't want to have the spaces, the income having these strong properties from the lower line, but you are fine with just getting all of the same property, and as an income as an outcome. Then under U above D, U is the minimal cardinality of a base of an ultrafilter. Menger property is not productive. And if you in addition assume that cofinality of the D is regular, you can get here X and Y such that all of their finite powers are Menger, but the product is not. And speaking of positive results, well, of course, big positive result was a Barman and Dow. There are more positive results. It's in the Lyubomyr model, the product of 2 Hurewicz spaces must be Menger. And the funny thing is that we don't know whether it's true for 3. It really just the proof works for 2, but what happens for 3, no idea. And then in the Miller model, the product of any 2 Menger subspaces must have the Menger property. But then, of course, the power of logic tells you that it's also true for 3, 4, and so on. And, well, this inequality between cardinal characteristics, I'm not going to define G because it will never appear in this talk again. But it seems that it absorbs most of the combinatorial properties of the Miller model that you need for the proof, but there is some slight moment that you really have to go and analyze how forcing works, and I don't know, maybe it's actually sufficient, that you don't really have to think about forcing, but just use this inequality, and then you can do it. The problem is that there are only very few models with this inequality. It's very hard to get it. And it seems now that the Miller model is very friendly to products, but not to products of Hurewicz spaces, because it turns out that the Miller forcing preserves gamma sets, and it preserves the ground model reals unbounded. And then immediately you get that in the Miller model you've got 2 gamma sets of reals whose product is not Hurewicz. So in particular, the product is of the Hurewicz property is not productive in the Miller model. Good. Now, which problems remain open? So is the Hurewicz property preserved by finite products of sets of reals in the Lever model? Remember that we have very weak answer to it, that the product of 2 must be Menger, but is the product of 2 Hurewicz? Let's go in the other direction. Maybe in ZFC you can have 2 Hurewicz subsets of reals whose product is not Hurewicz. And another funny question is, for any property you've got a critical cardinality, namely the minimal cardinality of a space which fails to have this property. And all the spaces which have smaller cardinality, they're kind of trivial examples. So it's always interesting to have examples having exactly this cardinality, because then you see that you can attain it. And for the Menger property, you always have a Menger set of size D, but can you get one which has all finite powers? Menger, and again, has size D. And if you get it, you will certainly get a Menger subgroup of the reals of size D. Just use these spaces as generators, and then the group will be just a countable union of continuous images of finite powers of this space. That's easy, but maybe you've got a group, but not a space. And it's known what to do if D is regular. So if you would like to construct a counterexample, just go to a model with D singular. And, well, you cannot say that, you cannot really get Rothenberger property that it fails by products outright in ZFC, because consistently all Rothenberger spaces are just countable. But now imagine that you've got a chance, right, to fail that the Rothenberger property is not preserved. The chance means that you've got an uncountable example. Can you get then one which has non-Rothenberger square? I think this is due to Arne Miller, and I think nobody has any idea how to do it. Okay. Oh, and more problems about gamma sets. So from that result of Barman and Doe, it's kind of natural to ask after you have it whether MA is enough to get the same result. Well, they used PFA, and if you go into the proof, it's really the stuff that really used proper forcing there. And well, maybe you've got from PFA something stronger, because you know that the product must be Menger. Maybe it actually you can get it Hurewicz. And well, if yes, is MA enough? It's the usual play. You can proceed here, but I guess you've got the idea what kind of questions you may ask once you have that result. Another funny question of Arne Miller is, suppose that you have a model of MA, and you've got a gamma space. So under MA, all sets of reals of size less than continuum, so are gamma spaces. And you've got another gamma space which has size less than continuum. Must the product be a gamma space? So why is it interesting? Because in all other covering properties that you have, well, if you have they are preserved by products with spaces of size less than P. P is the pseudo-intersection number, like the smallest of these cardinal characteristics people consider. So here you have a MA, P is continuum, you've got some small set. Actually, this is open even for Y of size omega 1. This is not known. And good, I guess I wanted to say also something about combinatorial versions of separability. I will not get far, but I will just tell you what is that about. So those of you who do Banach spaces must like the idea. It's like you embed the Banach space into the double dual. Well, people just say, oh, this is your linear functional. It acts, it kind of maps the element of your Banach space. But then if you think about the double dual, this is your linear functional, and it maps the element of your dual space. Now, the same play you can play with points versus open sets. You may just think, oh, can I cover this point by open set? But you may think, oh, can I hit this open set by a point? So this leads to the following notions, which are kind of dual to all these covering properties that are combinatorial properties, which are versions of separability. Let me just introduce a couple of them. It's M-separable, tells you that if you've got a sequence of 10 subsets of X, then you can select finitely many from points from each Dn such that their union is dense. Okay, and H-separable, the same happens, but actually in a very strong sense, that any open set in your space gets hit by Fn from some point on. Okay, and as an example is second countable spaces. It's very easy because you've got just countably many tasks. Even better, spaces with countable pi character are H-separable. And again, H-separable are M-separable because if you've got some stronger demand here. And countable Fréchet-Urysohn spaces are M-separable. And we don't know whether countable Fréchet-Urysohns must be not H-separable. So you may actually consider also these versions of separability. You may ask whether they are preserved by finite products. The same thing. You may ask whether they are preserved by unions, by going to some stronger topologies. And they're kind of nice because they are not only dual to the Menger property and Hurewicz in this very far, like using this very far analogy, but there is a precise duality coming from the CP theory, namely that the space for metrizable spaces, the space of all continuous functions on real valued functions on X with the topology of pointwise convergence is M separable if and only if all finite powers of X are Menger. And Bella, Bodenzynga, Matveyev proved that the same is true for Hurewicz. So, yeah, I guess I have to stop now. Thanks for your attention.
Some of these properties you've defined, we're choosing from a sequence of open covers one at a time, but we start looking at the entire sequence, correct? We have information about...
Exactly.
Okay.
We are given the entire sequence, yes.
So are there game theoretic versions of these properties?
For each of them, actually, people consider game theoretic versions. And what happens typically is that, well, the first player gives you some open cover, and then the second is allowed to do something. So if it's related to Menger, it selects finitely many, and if it's to Rothberger, select just one. So any of these properties, you've got a game associated to it. And now in most of the cases, the property is equivalent to the first player having no winning strategy. And that's actually very often used. There is a beautiful proof of Landro Aurici that Menger spaces are D spaces, like, which is unknown to be true for Lindelof, regular Lindelof. And for the second player, having the winning strategy is typically very, very strong. For Menger's property, it's sigma compactness. For Rothberger, it's being countable, and that's what happens here.
Yeah, okay, so that answers my second question, which is, so Luzin sets are not necessarily...
No, because they are uncountable, and if you're a set of reals and the second property has a winning, second player has a winning strategy in the Rothberger game, must be countable.
Okay, thank you. Are there any other questions? Okay, well then let's thank Lyubomyr again.